Yeah, hello and very welcome. My name is Wolfgang, Alper from Intelligent GmbH. And I'm very glad today to share with you the talk, Leverage Machine Learning for Detecting Anomalies, Zabbix meets AI. And we already had today a great talk about AI integration in Zabbix, thanks to Thomas. And this talk is a little bit different. This talk does not utilize ChatGPT at all. So the previous talk was more about like ChatGPT can assist you in creating configurations and assist you in better understanding your trigger messages or your error messages. This talk is really about anomaly detection, and we will walk through this. And I would like to take you on a journey, where the idea of anomaly detection using neural networks started. And for this, we have to go back like about 4 years. And in 4 years, the following happens. We have customers, and our customers are monitored using Zabbix network monitoring, of course. And one of our customers operates a web shop. In fact, they operate more than one web shop. And what happens was that this web shop got somehow hacked, and Zabbix unfortunately did not alert the hack. And the customer was not happy about this. And then we had a conversation ongoing that looked a little bit like this. And the customer said, why did the network monitoring not alert that our web shop was hacked? And we said that simply because Zabbix was not configured for this specific scenario. And then the customer says, well, if I go to the doctor and ask the doctor to take a blood screen, then the doctor can say there's something wrong with me. So why can't Zabbix do the same thing? And we said, again, it's just not, we didn't have any configuration for that. There was no trigger configuration. And then someone of our team says, just wait a minute, maybe we can do something. Maybe we can get Zabbix to learn specifics about a system in a sense that it understands that something is wrong with the system. And basically, that was the starting point of this idea about 4 years ago. And I would like to take you now on the journey of the idea of anomaly detection, to introduce a little bit the idea about neural networks, and finally to show you how we managed to implement all of this in Zabbix. So what's the idea about anomaly detection? Most of you, I mean, all of you are Zabbix users or Zabbix experts, Zabbix administrators. So most of you will have seen this sort of graph. So you see network traffic, you see CPU load, memory usage, and so forth. And basically, what you can say is this could be some sort of a blood screen of a system. And I think all of you will agree with me that it's very hard to write trigger conditions for this. So, for example, if the CPU load is above 100%, or not above 100, but maybe above 50%, then it could happen because maybe you have a web shop that just got hit by tons of visitors. Yeah? So it's not easy to actually define good trigger conditions just on these type of metrics. And so the idea that we had for the anomaly detection was that instead of having one trigger that looks to one metric at a time, maybe we need to look at multiple metrics at once. So we need to create a context across those metrics. And instead of using simple trigger functions or simple aggregate functions, maybe we need to look to the data as a whole and how the data developed over time. And instead of having static conditions in the sense of if the CPU usage is above like 50%, we might need variable conditions depending on the time of day or variable conditions depending on other metrics that we are going to collect. To give you a better example, what I mean with that is, take the first example, the very simple example, monitoring a server room. So we do not pay only attention to the temperature in this sense, which is temperature is above like 20 degrees, but we also put it in context with the power consumption of a system and maybe the air conditioning power consumption of the air conditioning system, and so forth. So we put all of the metrics together. And in this scenario, that looks a little bit different. For example, if the power consumption of the entire server systems in the server room increases because there's more load, then maybe the temperature will slightly increase, which is okay. It's not a it's not a failure in the sense. But on the other hand, if the power consumption of the system stays the same, the temperature increases, and even the conditioning system itself draws more power, then certainly we have a malfunction of the conditioning system. So that's the idea, basically. Another example would be the utilization, the server utilization of a server that, for example, manages user traffic and so forth. And if the number of users increases, certainly the number of the CPU and the memory use might increase. So basically, this is the idea. And the other idea is not to look for the moment, but to look to data over time. How does the data develop over time? So that's basically the idea. So how does it fit to machine learning and neural network? And before I step into this, I would just make sure that we are on the same page when we talk about AI and machine learning and so forth. And basically, AI is right now the overarching term used anywhere, and machine learning is just a sub-area of it. Yeah? And machine learning can also be implemented without AI. And then we have the term neural networks. And this term neural networks is often used in case of machine learning with AI for a specific type of how you create models. And deep learnings are just more sophisticated, complicated models in the sense of neural networks, just that we have some definitions here. And machine learning, so in this sense, is not necessarily based on neural networks or on deep learning. And a good example for that is that Zabbix, in the recent versions, added functions like, for example, trend STL, which is an excellent function which utilizes machine learning, but it does not rely on deep learning, for example. Yeah? And these functions are designed as they are right now in a sense that they work with time series data, but they work with time series data of just a single metric. So what they what they cannot actually do is they cannot create a context across multiple metrics. So we have machine learning right now in Zabbix available, and it's not always easy to use. I can say this, but it's there, but it's not able to create relations to other metrics. So there's no context to other related metrics. And to better understand what I mean by that, because it becomes important when we talk about the idea of neural networks, we need to understand simple data and time series data, so the definitions for that, and we need to understand univariate data and multivariate data. And don't be afraid, just a couple of slides, and it's immediately clear to you what I mean. So what is the difference between univariate data and multivariate data, and simple data and time series data? So univariate simple data would be just one value. Temperature is 23 degrees. Very straightforward, very easy to understand. That would be univariate simple data. If we have a list of values, like temperature was at 133 degree and 5 minutes later 24 degree, in this case we have time series data of just one specific metric. And multivariate data, if you put multiple different metrics together in a sense, like, for example, the last measurement was 23 degrees, humidity 56%, and so forth. There would be just multivariate data, but a simple data shot. And if you do it over time in pairs, like this here, like this, then you would have multiple metrics, and this would be multivariate time series data. And what we are interested in this scenario, because we would like to have a context across multiple metrics, and on the other hand, we would like a context over time. What we need for this is we need multivariate time series data. This is a JSON representation of the same thing, and I think most of you will is used to this one. Yeah. So we have our simple data sets here, which we, for example, can get from the Zabbix system, and we put them together. And then we have multivariate time series data. That's what we're looking for. And in this sense, we create a context, say that the temperature and the humidity and the pressure, for example, they somehow belong together. That's the idea of multivariate time series data sets. So how does it fit into the idea of neural networks? Well, a neural network in its basic form has what is called an input layer, a hidden layer, and an output layer. On the left side, you see a very basic example. You have two inputs, input 1 and input 2, and these inputs are connected then with a metric. Like, for example, input 1 would be the input for temperature, and the other one would be the input for humidity, just to say. And then you have some hidden layers, and these hidden layers are then connected to an output layer, and the output layer creates some sort of output, whatever you're interested in. The right-hand side, this one here, shows a more complex example and has different outputs. In this scenario, we have 3 outputs. And just to give you an idea, each connection here represents some mathematical algorithm that is a little bit more complex. And this means that this network already, in this configuration here, has to train 46 trainable weights. So if you train this network, it will create at minimum 46 trainable weights, and that doesn't even account the biases that are trained on top of that. So it's quite complex. It's not just a simple thing. For our approach to get access to a context over time and to get context over the metrics, what we are looking for is a special type of neural network or deep neural network, which is called an LSTM autoencoder. And you've heard the term LSTM just a minute ago in the other talk about AI. And Thomas mentioned that LSTMs are good to recognize things over time. They have a memory, and that is the reason why they are called long short-term memory cells. And we're using the same thing, by the way. So we're using LSTM cells to get the temporal context over time. This is how each of these connection points looks in detail. I don't want to walk into this because we do not have that much time. But you will clearly see that it's a complex structure that each of these connections represents. Yeah? And all of these LSTM cells have their own memory and can keep this context. So autoencoders are a perfect fit for that. How does this autoencoder idea work? What we do is we have an encoder component here, which is this one. And then we have a decoder component, which is this one here, this hidden layer 3, for example. And what the encoder tries to do, it tries to compress all the features into this small area in the middle and then extract the area. So basically what it does is it tries to learn the specifics of this data type. Pretty much the same thing if you're using an MP3 encoder to compress a WAV file, for example. Then the MP3 file is much smaller than the original WAV file. Yeah? It sounds similar, but it's not the same file. And basically that's the idea what we do. And if I take this example of this MP3 file and put it to the end, if you put something else to an MP3 decoder, so not an MP3 file, but for example a JPEG image, then the reconstruction will fail. So the MP3 would not be able to create some WAV file out of it because it's the wrong input. And basically what we're doing is we train our network with data that looks good, and then we ask the network to recreate that data, and if we have a recreation error, then there must be some anomaly in the data. That is the basic idea behind this autoencoder technology. So basically what it does, it acts as a data compressor. So what we have now together is we have an idea about how a deep neural network should look like for anomaly detection using time series data. We have the time series data by themselves. We can keep temporal context, and we also can have contextual relationships between the data or across all of the data. So the next step, what we need to do now is we need to think about how do we train such a model. And basically, training a model these days is for us at least, is the biggest challenge because you need good training data. In a perfect world, you would have good labeled training data. And what we were looking for, that was one reason for the approach using this LSTM autodecoder technology, is that usually the supervised learning requires labeled data, which is not always easy to get. And this autoencoder strategy allows us to do an unsupervised learning in the sense of that we just fit data to such a model from our Zabbix environment where we know that there's no issue at all. So we just fit this to the model, and then the model would be able to detect that there's an issue later on, which is excellent, which makes the process so much easier. So how do we prepare the data for training, testing, and inference? So just to set some term, to train a model means the model learns the specific of the systems, and inference is a process if you actually apply data to that model for real-time analysis to see whether there's an anomaly or not. So training is to train a model, and inference is basically to use the model. So we have 4 phases we need to have a look at. Extraction, so we need to extract the data from our history data from Zabbix. Usually using the Zabbix API is a great way to do this. Then we need to enrich data. What do I mean by data enrichment? Enrich data means that we need to provide additional context to a model when the data itself does not provide such a context. And a great example for this is a timestamp. If you have timestamp data, then the timestamp will just increase over time. Every second, the timestamp will increase. So the model does not understand whether it's a Monday, a Friday, whether it's 11 o'clock or whatever. So we need to split this timestamp into something that a model can understand. And that is data enrichment. This process is called data enrichment, and that applies to different areas. But for our view here, we will create additional inputs out of the timestamp. Then we need to normalize the data in a sense of that the network understands and it can deal with it, that we can train the weights and biases in our network properly. And finally, we need to window our data, so we create chunks of data that can be processed so it gets the temporal context. And we will walk through this one by one. So extraction is very easy. We decided that the simplest way to do it is to use tags. Zabbix added tags a while ago, and thank you for that. You can just tag anything. You can tag items. And we decided you just apply a tag like AI to an item, and then the system knows that this data should be extracted. And if you then use the Zabbix API, you do some sort of request, and then you get something back like this, which is excellent. The next step is data enrichment, and I mentioned this time series thing as an example for that. So what we do is we take the timestamp here, and we convert the timestamp into something that a neural network can understand, with the idea that it should learn whether it's January or whether it's February and so forth. And the best way to do it is to apply the sine and cosine function to this. So we get a periodically a graph or information for the network that it understands the periodicity over time. And you can apply the system for the week, for the day of week. You can apply the system for the month of year and for the hour of day and so forth. And with this technology, we split, for example, one value here into multiple inputs, but the network all of a sudden can understand this was a Friday, this was a Saturday, this was January, and so forth. And we need to do actually both sine and cosine here, because if you look to this value, for example, here, like 0.5, then this value shows up on this graph, but also on this graph and here. And if you do both sine and cosine, then you have a very specific position on the graph, and so the network understands really what's going on. The next step is data normalization. We need to normalize the data so that the training process will be efficient. And normalization just means that we take our data from the data set and put the values of that data, whatever that value is, to something between -1 and 1. That is the best space for a network to be trained. And if I go back a slide, you see the sine and cosine function automatically gives us the advantage of having the data scale to -1 and 1. So this is data normalization. And finally, we need to do some sort of windowing. So we need to send chunks to the neural network so it understands the temporal context. And we need to do it later also when we are using the model for evaluation or inference, when we actually pass data to the model. So we get a set of data that looks like this. Yeah? So we take this one here and convert it in such a way that the data has been prepared to pass over to the network. And when all of this is done, we create chunks of values, each representing a metric like this, in a window, and put this entire window then to these inputs of our neural network. And because we're using this LSTM-based network with memory, the network understands the flow of the data. Yeah, it will understand this and will see this. So this is a theory behind time series anomaly detection in general using neural networks, and now we see how we can apply this to Zabbix. And the building blocks are here. The first thing is we need to create a model configuration. So we need to define how the model looks like, and that also requires to set up the model type. In our case, it's an LSTM-based autoencoder model. It's the most best one. And then models can have what is called hyperparameters. Hyperparameters are, for example, the window size, how long are they trained, and how much inputs have they, and how are these hidden layers organized, detailed stuff. Then we need to extract training and test data to train the model, and test data finally to see whether the model behaves in a way that we expect the model to behave to. Then we need to create and train the model with inputs and adjusted match item from Zabbix. And then when we test the model, we would like to use existing historical data from Zabbix to make sure that everything works as expected. And finally, we would like to deploy the model and use live data on the model. Now the question comes, how, if we do all of this, how does Zabbix finally understands what the result of the evaluation of such a model would be? And the idea we had was very easy. We would just create a metric in Zabbix, an item, so to say, representing the probability of an anomaly. And then you can apply standard trigger functions in Zabbix and work from there. Yeah, and of course, this system should be able to run multiple models at once, because if you have a Zabbix infrastructure, you will have most probably more than one host, and therefore more than one requirement to detect anomalies. This is a very high-level view about how it works. So we have an AI training process here. In fact, we can scale up any number of training processes horizontally. Each training process requires a model configuration and training data. And the result will be a trained model. Then we have AI tester processes who take the trained model and use it with prepared historical data to see whether the model behaves as expected. And finally, for inference, we have the AI runner, which takes the live data from Zabbix, evaluates the data, and sends back to Zabbix the probability of an anomaly of such a system. Do you remember the time travel that I invited you initially? Well, this is how the data looked at that time. This is the data from the shop when the attack was happening. This is how it looks like. And I think we all agree that it's really hard for human, at least for me, and I have some experience as a Zabbix trainer, I was told. It's really hard to figure out that this is something that is an abnormal behavior. Yeah? And the secret lies in the relation between all of these metrics together. It's not just one metric, it's how they play together. And this is the data. And if we would like to use this data and to create a model, well, what we do is we tag the data here to be data that should be selected from the training process. This screenshot also shows the items created to take the reconstruction error or the probability of an anomaly that's being sent back from the inference process. And which is sent back by the AI runner as an indication. And this is basically how the configuration of the AI model looks like. So you can see we have the architecture here. We have some hyperparameter like the window size, like the number of epochs we would like to train, whether we would like to clip outlier. Outlier means if you have something like a graph that spikes for whatever reason, then you might want to cut it down so it doesn't disturb the other values. So this is the creating model process. Then we do the training of the model, and the training is basically that we take training data, and for that we define one or more hosts that we would like the training data taken from. And remember, because these host items are tagged, there's no further requirement to do any further specification. The system automatically knows what to take. And then we define the data range from what we would like to use for training. If your model should understand, for example, seasonality over an entire year, then you would have to train with data over an entire year. Other than that, it would not understand what is the difference between, for example, December or March. And then you can start the training, and you will see how the model was able to understand the specifics of your data, because this training, this loss function here, that is a term being used in machine learning and specifically in neural networks, define how good the model was able to understand what you feed to the model. And if the reconstruction error, the loss error is low, then the model performs very well. Yeah, so that's what you see here. And we can see that our model works fine. And this is the next one, where we do actually test the model. So we do apply now test data, not the data we trained the model with, but historical data we use for testing, and see how the model would work with this test data. And we can see the result of anomaly detection here. And these are different algorithms that can be used to do the calculation of the failure for a reconstruction. So just to give you an idea, let's say the reconstruction fails to recreate the temperature properly, or it fails to recreate the humidity properly, then you can define different mathematical algorithms to put all of this together and get one metric. And there are some specifics, some definitions, and we do implement all of these functions, and then you can make a choice. You will see in a minute how it looks like. So finally, you would like to use a model, and this is where you configure the usage of a model in production. You select the model definition, and then you select the AI runner where the model should be executed on. That could be a CPU-based system, or could be a GPU-based system. And finally, that is the output in Zabbix. That is how it looks in Zabbix. Yeah? So the model outputs. And that is basically done with a web shop data, by the way. So what we see here, we have here the reconstruction error using this mean absolute error algorithm, or the mean absolute percentage error algorithm here, explanation for what it looks like. And you can see here that we have some locations in the graph where the system detected an anomaly. Basically, the red ones here were the ones that we identified 4 years ago as an anomaly when we looked to the system and figured out that the web shop got hacked. Yeah? And after applying this model, we found this one as well. The model found it. We didn't see this. So maybe that was some previous sort of attack to figure out to do the final one. And you can apply to this metrics these trigger functions here, and from there it's as usual, business as usual. So to do a quick summary, and then I will end the talk. From our experience, deep neural networks are a great way to actually detect anomalies in time series data. And the deep neural networks really work great when you have multiple metrics that are somehow related to each other. And you can create a contextual relationship between them. And you can also use this stuff for multiple hosts, which means you can enable the systems to monitor entire services. It's not just one host that you can take metrics from. And because you can basically collect data from any system in Zabbix, you can apply this to any data from any other systems. Like, for example, you have a web shop and you would like to track the visitors, or you have a solar park and you would like to figure out whether your solar park is producing power very well. If you get the data into Zabbix, then you can use this AI idea to actually figure out whether there are anomalies. So I'm a little bit over time. Thank you so much. Hope you enjoyed the talk. Thank you.
Thank you, Wolfgang. So there's one question from Theo. So when the AI detects the anomaly as anomaly, how hard is it to also tell why it detected, why it decided that this is an anomaly?
Yeah, that's a very great question, and that is something that's actually not implemented. So it can't tell you actually why there's an anomaly. It can't do it now. It could it in general. The problem is that we haven't done this yet. We are working on this, and maybe I can tell about this later in a year or so. It's just a question of having good labeled data. So if we would like to be able to explain why there's an anomaly, then we would have to have good data. We have actually beta versions in progress where we try to relate this to the metric we are looking at. Yeah? But at this time and point, this one works reliable, the anomaly detection, and the classification to give you an idea where it comes exactly from is something that is actually in development, but it's not finalized yet.
Okay, thank you.
Yeah, thank you.